All right. So our objective is to calculate the present value. Let's just say we would like to calculate the present value of each cash flow one by one and sum them up. So how do we do that? We can basically multiply each cash flow AK. Remember, now we are calling this AK A1, A2, A3, A4. We are going to multiply each cash flow with single payment present worth factor. Single payment present worth factor, which regarding number of years, and sum the present worth of them one by one. How do we do that? For years 1 to n, each payment size, each cash flow AK is going to be multiplied with single payment present worth factor for I% interest rate, periodic interest rate, for K years, right? So if it is made in the end of, if the cash flow is observed in the end of K years, you are going to discount it back for K years to calculate the present worth. And you are going to do this for all years from 1 to n. For all years from 1 to n. And what is this formulation? P over F. It is basically 1 plus I to the power minus K, right? So single payment present worth factor is 1 plus I to the power minus K. And how do we compute AK? Remember now, in the end of year K, the cash flow size is the base payment times 1 plus F to the power K minus 1. So we write, instead of AK, we write A0 times 1 plus F to the power K minus 1. And we have 1 plus I to the power minus K. Okay. Now, instead of 1 plus F to the power K minus 1 here, okay, I am sorry. Instead of writing 1 plus I minus K here, I am going to multiply this 1 plus I with 1 plus I to the power minus 1 and divide it to 1 plus I to the power minus 1. Okay, so I am just going to add one additional 1 plus I here as a multiplier, and I'm going to divide it to 1 plus I again. If you do that, you will realize that the power of 1 plus I is also going to be minus K plus 1. And there will be an additional 1 plus I to the power minus 1 here. Okay. And because 1 plus F and 1 plus I is going to have the same power as K minus 1 and minus K minus 1, which is minus K plus 1. In that case, you can write them as a ratio and take the power of K minus 1 like this. So one has a negative power and the other has a positive power. However, we need to add a 1 plus I to the power minus 1 as a multiplier additionally. Okay. Now, this term A0 times 1 plus I to the power minus 1 is independent of K here. So I am just going to take this as A0 over 1 plus I outside the summation. And I will call this ratio 1 plus F over 1 plus I, which is the annual inflation factor divided by the annual interest factor. This ratio is going to be called X. So as K changes from 1 to n, we will have X to the power 0, X to the power 1, X to the power 2, X to the power 3, so on and so forth, until you plug in the last term n, which is going to bring you an X to the power n minus 1. Now, my objective is to calculate the sum of this value. Okay, the sum of this 1 plus X squared something something. Okay, so I need to calculate this summation. First of all, if I and F are equal to each other, if the inflation rate and interest rate, so this is not the inflation rate actually, F is not the inflation rate, it is the increase rate of change in the cash flows. Okay, so please let me correct myself. If I have called F to be the inflation rate, it is not, it is the rate of change in the cash flows, as you can see here. It is the rate of change in cash flows. If the interest rate and the rate of change in the cash flows are the same, in that case, 1 plus F over 1 plus I is going to be equal to 1, and all X values are going to be 1, and we are basically summing up 1 n times here. So in that case, if I and F are equal to each other, X is going to be equal to 1, and this summation in the square bracket is simply going to be equal to n. However, if I and F are not equal to each other, then this summation is formulated as 1 minus x to the power n over 1 minus x. Now, actually, I'm not going to explain this to you because I have already explained this geometric progression in earlier chapters. If you check the second chapter, you will see that I have already shown that this summation is equal to 1 minus x to the power n divided by 1 minus x. Okay. So when I is equal to f, the summation is equal to n. When I is not equal to f, the summation is 1 minus x to the power n over 1 minus x. Now, therefore, remember now the present word here is equal to a0 over 1 plus I times 1 minus x to the power n over 1 minus x. If the rate of change in the cash flows is not equal to the interest rate. If they are equal to each other, it is simply n times a0 over 1 plus I. Now, remember now, x is what? X is 1 plus f over 1 plus I. So if I plug in a x values as a formulation here, if I write 1 plus f over 1 plus I in place of x here, after a little algebra, you will realize that the present word will be equal to a0 times square brackets 1 minus the ratio between 1 plus f and 1 plus I to the power n divided by I minus f. So the above formula will become like this, and the below formula will not be affected because it is not affected by the value of x, because when f and I are equal to each other, x is simply equal to 1. So this is the present word formulation for the gradient series. So if you, geometric gradient series. So if you get a question based on geometrically increasing or geometrically decreasing cash flows, in that case, you can use this formula to calculate the present value of this cash flow structure. Now, once you calculate the present worth of these cash flows, you can also convert the present worth to the future value. In fact, you can also calculate the equivalent uniform series as well. So if you calculate the present worth first, then you can use the single payment compound amount factor to convert that present worth to the future value, or you can convert this present value with capital recovery factor A over P to the uniform payment size. So you can also convert this geometrically increasing series of cash flows or decreasing series of cash flows to what? To a uniform series of cash flows as well. Now, let's see. Consider, so we are going to solve a question based on that. However, before solving the question, did you understand my point of view in this problem, in this geometric series? So why does the geometric series exist? Why such cash flow diagrams are existing? Because at every year, my friends, your retirement salary is going to increase by a rate of increase, which is usually going to be based on the inflation rate. Actually, it is going to be less than the inflation rate, but it's going to increase at every year. So actually, this basically determines the amount of money that you need to collect in your savings account, if you want to take your retirement salary throughout your remaining years. So we are basically trying to calculate the necessary amount that should be accumulated in your retirement savings account, so you can get your retirement salary. Anlayabildik mi arkadaşlar geometrik serinin ne olduğunu? Takip edebiliyor musunuz? Okay. Now, let's solve this question. It says, consider a geometric sequence of cash flows where the first end of year payment is $1,000 and the rate of change in each consecutive year is 20%. Okay. So the first end of the year payment is $1,000, and in each year, the cash flow is going to change or increase by 20%, it says. So this means what? In the end of the first year, the payment will be $1,000. In the end of the second year, it is going to be $1,200, 20% increase. In the end of the third year, it is going to be 1,440. Why? Because the 20% increase is calculated based on the previous payment, okay, which is 1,200. Now, under annually compounding interest rate of 25% per year, so we have a 25% increase in your savings account. The question asks us, compute the present worth, future worth, and the equivalent annuity for 4-year payment plan. So we have a 4-year payment plan, my friends. So let me draw it to you. We have a 4-year payment plan. Like this. Okay, 4-year payment plan. And in this cash flow diagram, we have $1,000 in the end of the first year as the base payment. We have $1,200 in the end of the second year. We have $1,140 in the end of the third year. And here we will have 1,440 times 1 plus 0.20. So this is also going to be multiplied with 1.2. So every year, the geometric series is increasing by 20%. So the question is telling us this. What is the present worth equivalent of this money? So what is this? Or what is the future value equivalent of this payment? Or instead of taking a geometric series like this, if I convert this to a constant equivalent A values, okay, what is the equivalent annual payments corresponding to this geometric series? So it asks us to calculate all of them. However, actually, you only have a single formulation which calculates P, the present value based on the geometrics. So we will convert this geometric series to P first. Then, by multiplying P with a single payment compound amount factor, we will calculate F. And by multiplying P with a capital recovery factor for uniform series, we will calculate the annual payments. So let's calculate the present worth value first. Present worth. So I am going to go back to slide again. So we have a geometric series where the first year's payment is 1,000. So 1,000 is A0. This is the base payment. And the rate of change is 20%. At every year, F is 0.20. Initial payment, base payment is 1,000, and 0.20 is the rate of change in the payments. The interest rate that we are subject to in this payment plan is 0.25 per year, and the number of years is equal to 4. Now, how do we compute the present value? Now, remember the formulation. The formulation is this at page 32. If I and F are equal to each other, you use this formula. If I and F are not equal to each other, you will use this formula. So here in this question, I and F are not equal to each other, as you can see. Therefore, you use F as 0.20, the rate of change in the cash flows, and I is the decimal interest rate for this investment plan. And 1,000 times 1 minus the ratio between 1 plus F and 1 plus I to the power 4. 4 is the number of investment years, divided by I minus F. So as you can see, we have a positive I minus F here, will bring you a $3,013.07. So what does that mean? So my friends, this means this. So right now, if you have $3,013.07 invested here for the following 4 years, from that account, you can withdraw $1,000 in the end of the first year. In the end of the second year, you can withdraw $1,200. In the end of the third year, you can withdraw $1,440. And in the end of the fourth year, you will withdraw 1,440 times $1.2. Okay, so I will not calculate that one. So did you get it? So if you have this amount of principal invested in here, under 25% interest rate, you can withdraw this amount of money. So this is somehow a retirement plan for 4 years. Now, the next question is this: what is the future worth of it? Now, because you know the present worth, you can multiply the present worth with single payment compound amount factor of under 25% interest rate for 4 years to calculate the future worth of it. So, in other words, okay, so you can only see the, okay, I haven't shared the presentation, right? So let me share the presentation now. Okay, I'm sorry. The question is asking me the future worth. Okay, so I have calculated this 3013 and I was explaining this. However, I haven't shared the presentation file with you. Now it is being shared. The future worth will be calculated as what? By multiplying the present worth with the single payment compound amount factor for 4 years under 25% interest rate. You can check this value from the tables, and it is going to be 2.4114. And this means the future value of the same amount of money. So this is the total amount that is going to be accumulated in that savings account. Or the question is also asking what is the equivalent annuity. So it asks us to convert the present worth to annual payments in the end of each year. So you multiply the principal with the capital recovery factor, and the multiplication will be 1,275. So this means what? Instead of withdrawing 1,000 in the end of first year, 1,200 in the end of the second year, 1,440 in the end of the third year, and 1,440 times 1.2 in the end of the fourth year, instead of that, you can withdraw $1,205 in the end of every year for 4 years. But this is going to be a fixed amount, a constant amount. So the geometric gradient series uniform equivalent is this. This is the uniform equivalent, uniform payment equivalent of these geometric payments. So a nice question can be asked in the midterm exam like this. Now, this is the last question that we are going to solve today. So let's see. It says to a savings account, an engineer is going to deposit $100 in the end of the first month. And for 3 years, the amount she deposits in the end of every month will be 95% of the previous deposit. Okay. So the engineer is going to deposit money for 3 years in the end of every month. In the end of every month. And the first month payment will be $100. Then every month, the amount that the engineer is going to pay will be 95% of the previous deposit. Okay, so let me draw the picture. Okay, let's read the question, then I will draw the picture. If the nominal interest rate is 4%, the interest compounds monthly. So this is the nominal interest rate. Be careful. The yearly nominal interest rate. The interest compounds monthly, then the effective monthly interest rate will be 12 by 12, which is going to be 1%. How much money accumulates in the end of the third year? So what is the total amount of money accumulated in the end of third year? So let me draw the cash flow diagram to you. So we have, sorry, it's a little, okay. So we have such a cash flow diagram here, and it consists of months, okay? And in the end of the first month, I am going to deposit $100. In the end of the second month, I am going to deposit $95, which is 95% of the previous payment. In the end of the third month, I am going to pay 95% of the $95. So I'm going to multiply 95 with 0.95. So let me write it like this. 95 is going to be multiplied with 0.95. And it is going to go like this until the very end. In total of 3 years, which means there are 36 months here. For 36 months, I will first deposit $100, then $95, then 95% of the $95. for every consecutive month, I am going to pay just 95% of the previous payment. Okay? And this is going to continue for 36 consecutive months. It says for 3 years, 36 months. What is the effective interest rate per month? I. It is R over M. The nominal interest rate, which is 12%, divided by the months, number of months, which is 12. So it is going to be equal to 1%. 1%. So this is my effective interest rate. So there are 36 periods. 1% is my interest rate. And I have a geometric series. However, this time the rate of change F is equal to what? Minus 0.05, right? So every payment, every consecutive payment is 5% less, 5% less than the previous payment. So let's go back to the presentation now. So my base payment, the initial payment in the end of the first month is 100. My rate of change in my payments is negative. It is minus 0.05. My effective interest rate per payment period is 0.01, and there are 36 payments in this payment plan. The present worth will be calculated with this formula because the rate of change in the cash flows is not equal to the effective interest rate. They are different. And you will realize that here, when you plug in the rate of change as minus 0.0, arkadaşlar lütfen çok dikkatli olun. Bakın 1 artı F diyor ama buraya eksi olarak yazmış değil mi? Buna dikkat edelim. Eksi olarak geçirmiş buraya. 1 artı F burada eksi olarak geçmiş. Neden? F negatif çünkü. Aynı şekilde aşağıda da 1 eksi F diyor ama eksiler birbirini artı yapıyor. Yani diyorum ama bakalım. Hayırlısı. In the end, when you calculate the present value, you realize that the present value of this 36 months payment plan is $1,482.87. And the future worth is what? The question asks you the total accumulated amount in the end of the payment period. The future value is the principal amount times the single payment compound amount factor for 36 months under 1% interest rate per month. So you are going to multiply the principal amount with 1 plus 0.01 to the power 36. Remember now, monthly effective interest rate is 0.01. You are exposed to monthly compounding in the question, and you have 36 periods until the end of the investment plan. So the total accumulated amount will be $2,121.64. All right, so that's it for me today.